Yeah, I think it's okay. So good evening. This is the 12th tutorial session on NPTEL course on finite element modeling of welding processes. So this is going to be our second last tutorial session, and let's just turn off our screens just for bandwidth preservation. Yeah. So in the last session we had talked about the last session we had talked about setting up a problem in Phoenix. On Blair, this one. So it was on. We're looking at this problem. So the screen is visible, right?
Yeah.
Yeah. Yeah, we'll just once go through because I think we were able to obtain this weak formulation, right? This equation here. So the goal is to discretize it so that we can write this problem as this will be our mass term or the inertial term, and this will be the stiffness term because stiffness is ultimately related to stress, isn't it? The internal stress.
Yes.
I mean, the stress itself. And then this goes as the forcing factor, the forcing term, this body force as well as the traction applied on the bond. So this we can write in terms of this bilinear form, or so that is what essentially the goal is. Once we discretize it, then it becomes of this form, and then it's purely a time dependent problem post this. So here M is the symmetric bilinear form associated with the mass matrix, and K is the one associated with the stiffness matrix. So after introducing the finite element interpolation and all into this problem, like we will use this Galerkin approximation, do all the assembling and everything, then we get equation of this form. It's just, yeah, you see, right? It's like V in terms of the expansion of that basis functions. So, and then this V is just the coefficient vectors and everything integrated goes within this. Likewise for stiffness matrix. We'll do this in detail again. The finite element, I think we need to keep on revising it. Yeah, but for today, it's like we have been given V transpose MU plus V transpose KU and V transpose F. Now V is the arbitrary constant, sorry, arbitrary vector. So what we can do is we can take V transpose out, factor out. So what will be left with is MU double dot plus KU is equal to F because V is arbitrary. So if V is arbitrary, which means this holds for any V, because of which we can just delete V. It's just like, say if you have A into B plus A into C is equal to A into D, then you can, and if given that A is any arbitrary number, then it's equivalent to B plus C is equal to D, right? That just a simple analogy. I think maybe I think that actually that is the logic here also. So it's as if you have say A, B plus A, C is equal to AD, right? And given that all these are numbers, scalars, A, B, C, D, all are scalars. So what we can do is we can also write this as A into B plus C minus D is equal to 0. We can write this, right? Now, if A is arbitrary, then what happens is we can just delete. I mean, it's just like for this expression to hold for any A, the only conclusion that we can have is yeah, 0, yeah, exactly. So this same reasoning goes there also. Just that in that case, A happens to be a vector and B, C, D are vectors as well. So it becomes like A transpose B vector plus C vector minus D vector. Then the conclusion B vector plus C vector is equal to D vector. So right. So that is essentially the here also it's the same thing. We can just take out this. It will become mu vector plus ku is equal to f. So that is what we are essentially going to solve. But since in this case Phoenix handles all that conversion of what you call bilinear form into the equivalent matrix representation, that it does internally, so we don't need to worry about all those details because that is handled by Phoenix. Although we have certain functions which can with using which we can extract mass matrix and also extract stiffness matrix, also extract force vector from our bilinear form. There are functions. It's known as create matrix. So yeah, by that we can just extract what you call the required quantities from our bilinear form. Now since structures also involves all this damping and all, right? So because of it, we would also like to add some dissipation because structures do not oscillate perfectly, but they also tend to lose energy through various dissipative mechanisms. That could be friction with air or supports, internal dissipation through plasticity damage, etc. And the dissipative terms can be introduced at the level of constitutive equation if these mechanisms are well known, but quite often it's not the case. Now, dissipation can then be modeled by adding an ad hoc damping term depending on the structural velocity u dot to the previous evolution equation. So here it becomes find u vector is an element of v such that m of u double dot v plus c u dot v plus ku is equal to lv. For u, v is an element of capital V. So that is our bilinear form. Now here damping term is generally considered to be linear and symmetric because if there is a constraint on C, like if C is not symmetric and bilinear, then what do you call, then we have to like it becomes slightly tougher to solve it, slightly tougher. Then we cannot use all those symmetric properties and all. So in general, what you will see is in structures, what is done is we tend to have C matrix, which is the damping matrix, to be a linear weight of what you call linear combination of the mass matrix and K. So it's like C, this C here can be expressed as alpha M, alpha is a scalar into M matrix plus beta is a scalar into K. So that is known as Rayleigh, what you call Rayleigh damping, and this is very common in structural mechanics.
Okay.
Rayleigh came up with this just to exploit the symmetric because we don't have a perfect representation of damping. So just for exploiting all those properties of matrices, right? The symmetric matrices has a lot of properties, isn't it? That eigenvalues are real and eigenvectors are orthogonal. So those properties are very useful. So this is what is known as Rayleigh damping. So you see C can be expressed as a sum of M and K. And since M and K both are symmetric, then even C will be symmetric. And alpha and beta are scalars.
Okay.
Yeah, so these are like widely used. You in any mechanics literature, in any structural vibration literature, you also always see that Rayleigh damping is something which is very much used. It often makes it as if it's some sort of a hypothesis that although it cannot be proved, but you still take because of the ease with which it helps us to simplify our numerical process. And also we don't have an exact, we can never actually model dissipation. So we have to use
right?
such.
In the PDSM you can't, right?
Uh-huh.
PDSM you can't do, right? Real dissipation.
Yeah, exactly. Yes, yeah. Because it's very tough to measure unless it's for a simple system. Like say if it's spring mass system, then we can measure the time series and get the effective damping of the system. But if it is for a continuous structure, then we cannot do that. We don't have that much freedom or that much means to do all this. So that is the thing here, yeah. So that's what here you'll see a Rayleigh damping. It's so much well known that the author has provided us one small brief description that when little is known about the origin of damping in the structure, a popular choice for the damping matrix is the Rayleigh damping, which consists of linear combination of both. And these coefficients are actually obtained by fitting some experimental data and then obtaining eta m and eta k. One notable advantage of using such is that modes identified from the model analysis based on K and M still form an orthogonal basis, yielding decoupled evolution equations even in the presence of damping. This will require a separate session on basic vibration, so I think we'll do it at sometime.
Sure.
Yeah, because to decouple, like you'll ask the reason why we solve all that 1D oscillating system, right? Mx double dot plus cx dot plus kx is equal to f, right? The linear vibration equation. The reason is as we what you call look, I mean, as we will see that this equation like mx double dot plus cx plus bx is equal to f. So this is the 1D oscillator. 1D oscillator it is, also known as MSD system, mass spring damp system. Now this system, we spent a lot of time in structural vibration just because if we decouple even a complex system like say M, X, double dot, like there is a matrix vector system, no, there's for a general complete system that we can have for a 3D body, general 3D body, then we have KX. Is equal to F. So this is a general system. It can some what they call end of system. So once we discretize any general body and then convert into what you call spatial discretization and use all those finite element process, then we'll ultimately land with this or system of ODEs. And this, when you compare with this, right? As of now, you cannot use all the properties of here, but since M and K are symmetric, then we'll use Rayleigh damping approach to approximate our stiffness matrix. I mean this damping matrix. Then we will able to then even the C will be symmetric. Now we can use the principles from linear algebra. Linear algebra says that for a symmetric matrix, for an arbitrary symmetric matrix A, the eigenvalues will be real. Eigenvalues real. And eigenvectors are orthogonal, means one eigenvector will be orthogonal to the another eigenvector. So it's like you can move into a different space where the model, the basis function will be the eigenvectors. We'll talk about this someday later. Like it's a very beautiful concept of this the properties of a symmetric matrix, and we exploit the properties of symmetric matrix a lot, and we would always be happy if we have a symmetric matrix. Then we can exploit all the features of it, and then it helps a lot in even in numerical methods and all, because there are very good methods to solve symmetric problems, such as conjugate gradient method, which assumes that our matrix is symmetric. So there, once we use all this, then we can move into this equation. After doing some manipulations, we'll get some matrix, say M prime, and some vector, say U double prime. Likewise, this also C prime, a matrix, and then say U prime plus K prime, and then plus into U vector is equal to some F prime. Now you'll ask me, but okay, what was the need to do this? The thing is M prime, C prime, and K prime, they will be diagonal in nature. Now you see it's a very what you call nice this one, right? Reduction, that if these matrices are diagonal, then it's like you have just n number of ODs, right? N ODs which are uncoupled. Once it's uncoupled, you can use all those theory from 1D oscillator. It's like we solve n ODs independently and then assemble it project it back, which is like we have gotten the solution to this problem. So that is the beauty of 1D system. That's the reason we study 1D systems so much, because once after decomposing even a general matrix system, we are able to get a set of uncoupled ODs, and which are equivalent to just solving 1D harmonic oscillator system. So that's what is being done even here. Before that, they like in as per Phoenix, we have to discretize our matrix and then actually implement in Phoenix. So what we do is we introduce some time discretization of the interval 0 to 2n plus 1 time intervals with delta t is t by n denoting the time step. The resolution will make the use of Newmark beta method in structural mechanics. So as an implicit method, it's unconditionally stable for a proper choice of coefficients, so that quite large time steps can be used. And that is the thing with implicit method, right? That it tends to be unconditionally stable, provided that it generally tends to be unconditionally stable if it's an implicit method. So we want to use those ideas. So given that we have this discretized form, which for the time interval say tn and tn plus 1, we just want to solve for our values at tn plus 1, then we'll just write this equation for this at n plus 1th level. So that's what we say, m into u double dot n plus 1 u and n plus 1 dot plus is equal to f of t. In addition, the following approximation of the displacement velocity at t plus 1 are used as. So this is equal to un plus delta t un dot plus delta t squared by 2, then 1 minus 2 beta un double dot plus 2 beta u double dot n plus 1. So this is, these are the these two equations are actually the workhorse for Newmark beta method. So what we are doing is we are expressing our un plus 1, the displacement at un plus 1 using the displacement at the previous time step, the previous velocity, and some weighted average of acceleration at the previous and the current values. And this makes it implicit in nature, because even displacement at current time, I mean n plus 1 depends on the acceleration at n plus 1. Likewise for velocity, we have say u dot n plus 1 is equal to un dot plus delta t and weighted of what you call acceleration at two different values. And if you see here, when you put beta is equal to 0, then it becomes un plus 1 is equal to un plus delta t un dot plus delta t squared by 2 un double dot. And this you will recall is just recall from our kinematics course, right? During class 11 or 12, I mean class 11, I believe. We used to write, right, that something s at any time, I mean the distance covered by a projectile.
UT plus RV square, yeah?
Yeah, at any time is the initial velocity plus the constant velocity, the distance due to constant velocity and due to acceleration. Yeah, that is the distance covered. So that is how we can relate it. Only for beta is equal to 0.
UT plus half AT square. Why do we have this additional u dot n times dt?
Yeah, these are like just we are constructing some numerical method just to give implicitness. Once we have implicit, then it becomes the problem. Then what you call choosing time step becomes less burden. Like we have more freedom in choosing time step if it's implicit method. That's the reason right now we have put. But if you put beta is equal to 0, then this is the only term left, right? This one, because this one goes away, so it's like 1 into n, and that is like, yeah, it's like constant acceleration, constant velocity, and some initial velocity gives us the total, what you call the total distance covered. And likewise, even for velocity to increase, in that case, we have gamma is equal to 0, and it becomes u dot un dot plus delta t in un double dot. So it's just like some constant acceleration is going on, and then that was for explicit method, but for a general method, so that is what we call it. And that's the reason you'll find Newmark methods also being called as Newmark beta, because here this beta tends to be a very important parameter here, although gamma is also there, but the method is usually called Newmark beta methods. This was developed long back in 1959 by Newmark. You'll ask why do we need this method? Why don't we you can use Ranjit-Kutta methods and all? The reason is because in Ranjit-Kutta method and all, we will see that you always have to have first order differential equations. isn't it? So it's like you will always have, you can only integrate the first order derivative, not the second order derivative. So it's, if it's second order derivative, then we have to convert into a system of first order derivatives. Then only we can integrate it. That means that all the methods that are used in say fluid mechanics, this, sorry, CFD, cannot be used then, because all those methods developed for CFD uses first order derivative, right? I mean, they have the first order derivative in time. So we, all those things like Ranjikuta, Euler, Crank-Nicolson, all of them uses are only developed for first order derivatives. So Newmark beta method, the advantage is you can directly integrate the second order derivative itself using this two-step process. And it goes through some level before, say, what we can do is we can, in from this equation here, we can express u dot double dot n plus 1 in terms of un plus 1 and all. Then we can put it here. Likewise, even for u dot n plus 1, we can take it everything out from here, put it back here. Then this entire equation will be in terms of un plus 1. So then we solve for un plus 1 and then use these expressions to get for u double dot n plus 1 and u dot n minus plus 1. So that is like the process that we have to do in while using Newmark beta method. So most popular choice is gamma is equal to half, beta is equal to my 4. This you will find in almost any paper. You'll see, you'll find this. These are the most used values for gamma and beta, which ensures that unconditional stability and energy conservation and second order accuracy. Now remember that energy conservation is not possible. The reason is because of the uh, because the method is second order accurate only, right? That's the reason. So although we have, but it's not. So then we, if you want to conserve energy, and also then there are methods known as symplectic integrators. I hope you have heard of this. I'll just, these are like,
yep, I know. Yeah, I know.
yeah. So then symplectic method integrators are the way to go if we really want to conserve our energy as during our simulation. So then we move in we perform integration in our variables are in Hamiltonian space. So in Hamiltonian space, the variables will be displacement and momentum.
Okay.
So we cast our problem in such that our equations are in momentum and the displacement are the two variables. So it's just like, I'm sure we had discussed sometime long back, right, about that Verlet method and all. So Verlet method is about that one only.
I know. Well, it is one of the symplectic methods, no?
Yeah, just a minute, huh? Just a minute.
Sure, sure.
Yeah, hello, man. It's just, yeah, sorry. Hello. I hope I am audible.
Yes, you are. You are.
Yeah. Okay. So, like, these are the most popular choice for parameters. Gamma is equal to half, beta is equal by 4. Yeah. So implementation we have been discussing every now once in a while. So it's like, yeah, we'll not actually code it. We'll just go through it. Yeah. It's like importing all the basic packages. Then these are the fundamental ones: UFL, MPI, 4Y, and Dolphin.
Yep.
So
Basic.
UFL is, yeah,
Basic.
UFL is to construct all those mathematical expressions, right? Using
Yeah.
some language. I mean,
Yeah.
and then
Is is it
Dolphin.
like okay?
Haha,
It's like some expressions, right? UFL is to change expressions from mathematics to sorry, normal
exactly,
to that.
yes.
Yeah.
Yeah, internally it will
You
change
have
into
a name.
mathematical
You have
expression.
a name for it, but yeah.
Yeah, actually UFL means Unified Form Language.
Yeah. Exactly.
Yeah. And Dolphin is the main workhorse because it's Dolphin package which contains everything.
Yeah. People
Like
have
it contains.
papers in this UFL, so they write UFL for some new FSI. I said they write and they will publish. But anyways, yeah. PhDs.
Uh-huh.
Yeah.
Yeah, so that is how it is. Yeah. The thing is because UFL has been, it's so extensive, right, that any calculations can be performed.
Yeah.
It even has automatic differentiation tools. Like we don't need to
Exactly.
differentiate and give
Exactly.
expression.
That's
It
what I'm
can
saying.
do it.
Automatic differential tools के बारे में I was talking about. Yeah.
Uh-huh. That's the reason. Yeah. So like once we do this, then this Dolphin, like FEM is for constructing everything, function space and functional space, creating functions. It will all be contained, setting up the solver, all are in FEM class. IO is for handling input output, which is writing files and etc. Mesh contains all the mesh resources like create box, cell type, and what do you call other aspects of meshing. So it like when we use create box, we can create some locally we can create meshing of a simple box. So in that case, we have to prescribe the endpoints. So that the endpoints of the major diagonal and which passes through origin. That is what we do this main diagonal, and then we have prescribed the number of elements along x-axis, y-axis, z-axis, and which cell type. Then we here we have chosen hexahedron cell type, which is that brick element we call it in FEM. Brick element means 8 nodes. So brick has 8 nodes, right? So which means 8 vertices, isn't it? A
Yeah.
cuboid has 8 vertices. Yeah. So that's the thing. And dim is like domain.topology.dim. So it will give us the topology of this the topological dimension of this domain. So it's since it's 3D, so the dim value will be 3. And then we prescribe what should be the expression for the integration vertical variable with integration element, which is dx is equal to ufl dot measure dx domain is equal to domain degree, and then so this is like defining that integral, right? So if it is say f dx, so this is the dx that goes. This is an integral element, integration element, and degree to because what degree we want for our polynomials. So we have chosen quadratic polynomials for what do you call for our as basis functions, right? So that is how we have constructed the functional space over the domain V. Over the domain, we have constructed functional space. Q is some quadratic element because Q for quadratic, and it will take degree 2, and the shape of that one will be 3. Because the thing is, since we are solving a 3D problem, so at every point, the value of the variable happens to be a vector, right? U the VW, like it will have 3 displacement components at every point. So that's the reason. So this function space consists of quadratic elements whose shape is a vector at every point. The reason is because we are solving a 3D problem and it will have 3. The number of variables are, we are solving for displacement, which happens to a vector at every point. And view is equal to fem dot function. So now we are actually, first we define the function space. Now we define one function based on that, and which we named as displacement. Once that is done, now we'll just determine, we'll locate certain the values of which are on the left hand side, which means the so if this is that this one, right? So on one side, one face and this front face, because we want to apply the boundary conditions. So what we'll do is these are just to locate all those points which are on the left hand side and which are on the right hand side, and using this we can actually get all the degrees of freedom. So FEM locate DOF geometrical, and we'll just get all the degrees of freedom, and then we'll prescribe some Dirichlet boundary condition which are just happens to be 0 at those points. So that is the goal here, FEM dot Dirichlet boundary conditions, and on the clamped ends only we want to put the values of displacement vector to be 0. So clamped offs and V is our function space. So once that is done, now we go on to describe the solid mechanics part, which is Young's modulus. We define it throughout the domain, then Poisson's ratio throughout the domain, density throughout the domain, the forcing vector to be 0 throughout. So lambda and mu are the Lamé parameters. Then we define a function for epsilon,
Krishna,
which is the
I
symmetric.
have
Yeah,
to go at 6:30.
sure. So
So
it's, yeah.
shall
Okay, so
we?
it's like, yeah, we can just I think, yeah, we can do it again next time. I think that
Okay.
in our next session, I think that should be uh, good enough. Maybe I'll just stop sharing. We'll continue this
No.
on.
You can record it. I will exit. Maybe if you need some more time
Okay,
to
what we'll
record
do
and
is we'll continue it in our next session. I think that would be worthwhile. So let's continue in our next session. I'll just stop recording. Let's meet in the next session. Yeah. So,
Okay.
yeah.
Forces
Do not need to
need
be
not
equal
be
and
equal and
opposite.
opposite. You see? You understand?
Okay, so this is more general, right?
I don't know if like how to. I don't know how to say general and everything, but
Because the thing
so
is,
it's
then
not.
bond based will be a special case of state based, right? Because need not be,
state
yeah.
based, so in state based we don't have equal and opposite, but in bond based we have equal and opposite.
Yes,
I
yes.
don't know
So
which one is
I mean,
superior. I don't know.
no, the thing is state based is superior because the thing is it said need not be. So there is no requirement per se. If it is there, it's fine.
Okay.
Yeah.
Yeah. That's true.
Yeah.
But you
So
understood the
just,
point, right? What I'm trying to say,
yeah.
like in equal
Yes,
and opposite and
yes.
everything. So
Mm-hmm. Okay, so it can handle asymmetricity, right? In the force system, in the force mechanism, right? So like, although you are what do you call influencing other body in one manner, the other body need not influence you in the same manner, right?
correct. That's what he says. But the point is,
Yes.
it essentially breaks so many physical laws because, say, you are in,
Yeah.
of course, right? Because in stress, while we are deriving stress in our control mechanics course,
So in this
we
case,
have
the
said,
stress matrix, if it, I mean, the thing is, peridynamics doesn't have stress matrix, but say if it were
yeah,
existing, then it would not be symmetric.
correct. It is wrong. No, that's
Yeah.
what because in stress while you derived in our class, one of the tutorial classes, we
Huh.
discussed that it is equal and opposite. Like we have discussed all that stuff.
Right, right.
But here, if this is the case, then the other block, other cubical block, won't apply the same force or equal and opposite force on the adjacent cubical block, right? So that's what. But I don't know what they mean by this. And so you have to investigate a little bit more about the physical validity and the applications they are doing for the state-based. But the point is, first is bond-based, which is symmetric and everything.
Right, right. Yeah.
The second one is state-based. So here I have to flip it. So here,
Huh.
this is bond-based, and this is state-based.
Okay, yeah.
First is bond proposed, second is state. Okay, going back to the paper. So if you look at this, yeah. So here, this is how we compute the force.
Exactly, yes. You
You understand, right? So it's like the horizon. So you're applying the force on particle I. Okay. and you loop over all the particles of that particle like.
That is, yeah, within that.
Compute the force using this F.
Right.
This is force density, as we have seen from the yesterday few like last meeting. It's force density because you're multiplying by the volume, right?
I see.
You remember the MATLAB code?
Yeah.
And
So it was what do you call as force density, right?
correct. And the force density is computed using this equation. What is this? Say that you have. So you have initially block.
Yeah.
So you have some block like this. 1, 2, 3, 4, 5, 6, 7, 8, 16. We're trying to find the force on this particle say. Okay. So after the deformation, let's say we'll take these 9 points. After the deformation, say it becomes something like this. Trying to find the force on this. So these are the neighborhoods of the particle. Okay, so now initially, so the zeta here, if you observe, this S which you wrote is computed like this.
Yeah. That's what bond stretch ratio is.
Correct. That's right. So I think
this is just like the longitudinal strain that we look right
correct.
in.
Exactly. Yes. So initially you know the distance. After the deformation, you know the distance. So from this strength, you will compute the S value. And mu is a constant. C can also be computed from the microelastic modulus. I think it is given somewhere, or it's not given here, but yeah, it can be computed from the given geometry. Okay, and we can simply find the force. Once we know the force, simply use the velocity wallet scheme or any other scheme to move the particles. That's the predynamics algorithm. But the question to ask here, one of the questions, important questions to ask here is, say that these are deforming, the particles are deforming like this. Will the neighbors stay the same all the time? You understand my question?
Okay.
The neighbors, will they move like if they if say that you have this one-dimensional paradynamics problem.
Yeah.
Okay. Computing force on this. At time t equal to 0, this is the horizon. Outside this is the horizon. Okay. Equal to 0. After some time, say it deformed and they became too far away.
Right.
Since our horizon is always constant, no, like maybe 0.1 meter or something like that. If I again take the horizon, then only these 2 points will come in the horizon.
Okay. So the thing. So okay. Okay. So we cannot have a constant this horizon also, right?
I don't know. That's what I'm asking. So like we don't know. So I have to. We have to see some more literature, or we have to read upon it to know that if what is the case. So if we know, if we figure it out, then we are actually done. So the only part which is left to at least to simulate this 2023 July paper on period dynamics is, we know neta, we know zeta, we know this. Okay, we know S value also, we know mu also. We just have to know C value and we have to know this condition. Then we can simply take this problem and we can simulate period dynamics. Okay. One question is, how will we go like start to solve this? So here he has something called he took this L-shaped plate.
Yeah.
Okay. And this can be easily done. So like you take this and you discretize into points. Okay. All right.
Yeah. Yes.
Yeah. And you'll connect them with the horizon. You'll save the initial neta value or zeta value. Okay. And I think he's applying force somewhere. I don't know. Yeah, here he's applying displacement, I think. So this will start to move. As this moves, these points will also start to deform. and once this length increases to certain value, stretch value, we will see this is not in contact anymore. Like this bond will be broken. If this bond is broken, then it implies we will not consider that in the force.
I see. Yeah, yeah,
Computing the force. So that is the logic of this. But this is very hard problem. We don't. This has damage. We don't want to do damage because we don't need to do damage in the first place. We'll just do just a simple deformation, elastic deformation. We can take this elastic gate because in elastic gate, this problem. If you look at the simulation, so this is how it works. First it is constant, then it will move, Okay. Similar in simulation, you can see, right? There's no break anywhere. There's no fracture like here. Right. So we can start with this. So because here there's no damage, there is only elasticity. We can consider this case as a first example to simulate. This is a physical validation. Okay, I hope you're following. Yeah. It's not that complicated. Yeah. I think yes, yes. Really.
The thing is, once we introduce damage and all, right? So we have to have new, I mean, some time varying things as well. Like the material parameters themselves vary in time and all.
No, they actually don't. They don't actually matter. That's the beauty. Even though there is damage, the metal constants stays the same. But
okay, the thing is, okay, I see.
That's the point. Just I think to introduce the damage, I'm sure he writes it here somewhere. Yeah. So damage is computed using this. So if the S value is less than S0, like S0 is a damage parameter. This is how we compute damage. Okay. Then there is no damage. If it is exceeds, like if say that this is the initial S, so I think the S0 he computes maybe somewhere like this. So as the particles start to deform, so once
so these are like state variables, right? That it does not explicitly occur in the governing equation, but there are some parameters which depend on it.
That is correct. So they're like the external parameters. So we at every time we will check if our bond's S value, which is S value is here, the elongation, right? Stretch, right? S. Yeah. If it is exceeding or not. If it exceeds, then we'll say it is damaged, and we'll simply break the bond.
Right. Yeah.
So that is the point. This. Yeah. So I think that's it. So if initially you can just take some simple elastic beam like this. Okay. And apply some force maybe here. And from the physics we know it will deform, no, like this. We can check that with analytical solution.
Exactly.
And if you're so smart, then you can see how to. You can check some fracture as well and see if you have too much load, when it will fracture here or where it will fracture. That could be our starting point. So I will maybe next time we meet, I will just tell you how to write this in the code, or I will just write a simple algorithm and like whatever the for loop I wrote here. This thing, this for loop. I will show you how to write this in software and how to do the basic debugging or like code development. Then I think that will be good enough. But we need to know. So I'm just saying if I'm missing anything more, like am I missing anything like in this? That's what I understood with the reading I have had with this paper. I realized this is all we need to know. Just that the C value is missing. I don't know how he is computing this. C value is here, C value is here as well. So I've searched for the C value, micro modulus. I couldn't find anywhere. So that's the only value I think we need to. So the point here, the novelty of this paper is many people have already did SPH and thermodynamics coupling. So that's nothing new, to be honest. Okay. But the way he
Mhm.
pitched this paper is the way people pitch, like basically how they pitch the paper is. See, if you look, so the point is, I'll just tell you how he writes the paper. Okay, sure, you already know, but I just want to, yeah. FSI, SPH is very much used. Okay, SPH is used, and dual S physics couples with project chrono. So next time if we develop some software, we'll write pi peridynamics or pi SPH
Mhm.
peridynamics or something like that.
Mhm.
We'll put some name.
Mhm.
Okay, we'll say pi SPH
Okay.
peridynamics coupled with pi SPH, or we'll say one integrated software we develop peridynamics into pi SPH.
Mhm. I see. I
Okay,
see.
and we
Mhm.
will write like that. Then the point is, so he says like, so peridynamics. So but SPH and other numerical methods are being coupled, but not SPH peridynamics. So here he says peridynamics is good for fracture problems when the forces are large enough for failure, because SPH can't
Mhm.
handle that. Okay. Then he says, see, already peridynamics SPH models are already there. You can see these papers, and also peridynamics SPH papers are applied. You can see here. That's what he says. But in this work, then what it is already there, what I should do, like what we are doing new. What he says is, I think he says some correction. He did some correction. He added some new correction terms. That's what he says here as well.